Hello, I'm Aleks Juell, and I'll go through the Shale Well Optimizer Python project with you. This project consists of three parts. The first part is a single well shale finite difference model, where you can model either gas condensate, or oil systems. It uses either black oil or equational state CT formulation, and includes a very fine gridding around the factory. You can either model a full well or a single frac sector model. If you have tubing tables available, you can use them. Otherwise, you can use bottom hole pressures. The project is currently using the sensor reservoir simulator that can be customized for other simulators. The second part of the project is the production history matching module. Here you can history match gas, oil, and water production volumes and flowing pressures. The project performs an automated model tuning by changing reservoir and well model parameters like permeability, fracture properties, including fracture area and geometry. And the third part of the project is the well design optimization module. Here you can take a new well or an already history matched well and maximize the profit by changing well design. It includes a very flexible economics model to model well costs and profits. This first video will go into detail on the well model part of the project, and other videos will go into more detail on the two remaining parts. If you go into the well model composite, you can see first a grid definition file is read in to the grid generation utility. This utility automatically generates include files to be used by reservoir simulators that define the grid and the fracture geometry and the well completion. Then the reservoir simulator is launched on this grid, and the output files are collected. These output files are then converted into the screen format used by Python, so that results can be used for further downstream parts of the project. If we go into the grid definition and look at the parameters there, you can see that you can define all the well design parameters like the fracture, number of fractures, the fracture half length, the depth of the well, and all different reservoir parameters. This definition is then taken into the generate grid composite, where the grid utility is launched. This utility creates two include files: the initial inc and recurrent inc. If you go into the initial include file, have a look. This file contains the grid definition. Here you have the cell thicknesses in the x direction and in y direction. The matrix porosity is defined, and the permeability both for the matrix and the fractures. The reservoir thickness is also included in this file. This file is automatically generated, and the user won't have to do any changes there at all. The second include file generated by the grid utility is this recurrent include file. And here the well perforations are defined. These include files are then transported into the parent level, where the REST simulator is launched. If you go back there, you can see that the include files are transported into simulator and included in this main input file to sensor. We can go in and have a look at that file too. This model uses the implicit solver formulation, as you can see here. And you can define different maps that is printed in the output. The next part of the include file is where the first, the next part of, sorry, I guess that. The next part of the data file is where the first include file from the gridding utility is included, the one containing the grid. Then the rel firm is defined, and the PVT is included from a separate include file. Further on, the model is initialized, and the last part, or the last include file from the gridding utility is included, where the well perforations are defined. As mentioned before, you can include a tubing head pressure table if you have it available, as is done here. And then the well constraints are defined. The last part of the data file is the rate schedule and the end time of the simulation. If we go back to the project, as mentioned before, the grid is generated. The reservoir simulator is then launched on the generated include file, and the output is collected. And then the output is converted into stream format. And the rate and pressures are then transferred into downstream parts of the project. Then we go up into the top level of the project. You can see the model output data is being transferred into the two remaining parts of the project.